So we've completed the chapter 4, the process of design. And then in the chapter 4, we learned about the single cycle processor design and pipeline architecture design. So, so you need to remember why pipeline architecture is used in the processor design, and then this pipeline architecture design is so widely used. So most of the digital system adopt this pipeline architecture to improve the performance, its own performance. So you need to remember how the pipelining works. But I already mentioned in the previous class, the basic concept of this pipelining is very simple, and I believe everyone can easily understand the baseline concept of the pipelining. But the difficult thing is how to design the data forwarding unit or hazard detection unit. So actually, in order to improve the performance of a pipeline architecture, so we need to elaborately design this data forwarding and hazard detection. So it's a detailed architecture of pipelining is a little bit different. It's a little bit tricky. So I forgot that this famous idiom in the previous class, but so the famous idiom is that so devil is in the detail. 그래서 뭐 악마는 디테일에 있다. 이거가 굉장히 the famous idiom. 그래서 유명한 뭐랄까 격언이라고 해야 되나요? Famous idiom. So actually the detailed design, so detailed data management or control management in the pipeline architecture is a little bit tricky. Not a little bit, it's tricky. So because it's difficult to understand, and then also it's not easy to design the correct design. The correct design means that as we design the hardware works, so that is the correct design. But the many bugs or some mistakes can be included in our real design. So and then actually it's already true for programming. Actually, if we write some code, then our code will include the many syntax errors, bugs, and then so many mistakes. So we need to correct these mistakes and bugs, and then this process is called debugging. And then also the similar process is required for the hardware design also. So actually we are using our HDL, the hardware description language for lab assignment. It's very similar to our programming language, especially C language. And then so you need to debug your design actually, because your design, initially your design will include some bugs or mistakes, and then these bugs and mistakes will be maybe included in some pipelining control or some pipeline management design. So it is because the maintaining or some managing the data movement between pipeline steps or controlling the pipeline register is a little bit tricky. So actually the goal of the last lab assignment, so I believe today is the deadline of the third lab assignment. And then actually the goal of the last lab assignment is to design the pipeline processor. So then actually I believe sometimes it's tricky, but I believe the base concept. So actually, it's also applied to the hardware design. The basic design of the pipeline processor, I think it's not difficult. So someone may feel that, oh, it's difficult, but it's my opinion. In my opinion, so I believe the basic concept of the pipeline processor, also the basic design of the pipeline processor is not difficult. Okay, but the last lab assignment will include the design of data forwarding unit and hazard detection unit, but it may be difficult because it will change the basic instruction flow of this basic pipeline processor. So the correct design of this data forwarding or the hazard detection may be tricky. Okay, so also tricky means, so if this design is the tricky, then the related questions will appear in final exam. Okay, so try to understand how the data forwarding or hazard detection works in the pipeline processor. Okay. Okay. So now we can move on to the chapter. It's another important chapter of this course. This is the memory systems or memory hierarchy. So, okay. Introduction. So, what is the memory? What is a memory system? Or what is a memory? What is a memory system? Or what is memory in computer systems? Why do we need memory systems or memory component in our computer systems? Because we need to store data used by computer instructions. So actually the computer is the data processing hardware. So that means the computer reads the user data, and then this user data is used for the operand of the instructions. So we learned about the instructions in chapter 2, and then as you can see, every instruction requires operands like add, x1, x2, x3. So this add instruction requires 2 operands from register file. But where is this data come? Where does this data come from? It's from actually memory. So we learned about the data transfer instructions such as load and store. So load double word and store double word. And then using these instructions, we can move the data from memory to the register file, because these arithmetic instructions requires operand from register files. Okay. So actually the size of the register file is very small. So what is the number of general purpose register in the RISC-V in computers? RISC-V, yes, 32. Okay, good. The number of register, the general purpose registers in RISC-V processor is 32. So that means this size is very small. So when we when you use some very popular applications such as the Chrome web browser, then this web browser requires a large amount of data from internet. so it's from internet also. But we already know that the size of the data is very large. So let's think about the some movie files. So the size of the movie file is very large. And then actually the computer processor needs this stored data from in the actually in the network, like such as the Netflix or YouTube. But this data is given delivered to our local computer systems, like a hard disk drive. And then recently we widely use the solid state SSD, solid state drive SSD, not disk SSD. So this data is stored in the storage, and then the data is moved to the main memory of the computer system, and then also this data is moved to the actually register file inside of the computer system. But if you are interested in the real computer system hardware, or if you use the desktop computer, and then if you open the chassis of your desktop computer system, then you can find the main memory. So actually, in the computer system, this is the CPU and the main memory. So usually DRAM. Oops. DRAM exists out of computer processor. So that's why the DRAM is called external memory, not internal memory. And then actually this DRAM is the main memory of the computer system. So that means the data used by every instruction or every application is stored in the DRAM. Okay, it's a DRAM. This is actually the memory. So, and then I also in the chapter 2, I mentioned that every data used by computer processor, and then this data include the user data, also the program code. It's the text data. It's a program instruction, the group of instructions, and then this program code, also the temporary data, such as stack or some dynamic data is also stored in the DRAM. And then this all kind of data is transferred to the inside of the processor. And then also for this data transfer, we use the instruction called load and store. Okay. Then so this data is stored in the register file. Okay. So this how memory looks in the inside of the computer system. But in the chapter 4, we also learn about the architecture of processor. And then the weird thing is that, oh, there are two kinds of memory, right? So in the chapter 2, I explained that every data exists in the main memory, and then we cannot. And then I also explained that we cannot distinguish the different type of memory, such as the different type of data inside of the memory, such as the program codes or user data. So I already explained that these all kinds of data stored in the DRAM. So one memory. But the weird thing is that the CPU, the inside of the processor has two kinds of memory. Which memory? Instruction memory and data memory. Why? So what is this memory? So why do we use separated memory inside of this processor? 뭐 때문에 그러죠? Data header. In order to avoid structural hazard. So structural hazard is related to the hardware resource inside of a processor. So why? If the memory is occupied by data transfer instructions such as load and store, then instruction cannot be read from the memory. But for every instruction, so the processor need to fetch data from the instruction memory. So instruction memory is always used by processor, but if the data is accessed by data transfer instructions, then the computer processor cannot use the instruction memory. That's why we separate the instruction memory and data memory inside our processor. So why is it weird? So I already explained, every data is inside of the one memory. It's a main memory, but inside of CPU has the two different kinds of memory. What is this memory? So we will learn about this architecture of memory hierarchy. So this is called the memory subsystem, or this is called the memory hierarchy. So we will learn how the memory systems are organized inside of CPU, also the inside of a computer system in chapter 5. So actually this memory is the cache memory, not this main memory. So, so also we will learn about the cache memory in chapter 5. It's very important. Also, it's very critical for the performance of the computer processor. So we will learn about this organization of the memory hierarchy or memory system in chapter 5. So this DRAM, so main memory, is different from cache memory. Okay. Okay. Before diving into the world of memory systems, so we first need to learn about the data locality. So locality. And then this locality is frequently called the data locality. And then in Korean, the locality is translated into 지역성. 한글 책을 보면은 지역성 이렇게 나오는데 우리가 지역성이라고 이렇게 배워도 이게 도대체 무슨 말이야? 이게 알 수 없잖아요. 그렇게 쓰는 말이 아니기 때문에, 자주 쓰는 말이 아니니까. 예, 그래서 locality, 예, 그냥 직역해 놓은 거예요. 그래서 참 직역해 놓은 게 그렇게 또 이해하는데 많이 도움이 안 되는데. So anyway, so it is called 지역성 in Korean textbook, but in English it is called the locality. And then let's see what is the locality in data. 예. 그리고 이제 질문. 네, 캐시는 메인 메모리 내용을 복사해 놓은가요? 맞습니다. 네, 맞아요. So we will learn about the cache in the next class. Okay, so what is the locality? So locality, there are two kinds of locality in the data we use in the computer system. It's a temporal locality and spatial locality. So locality is actually related to the access pattern to our user data. So our data, the data accessed by computer program or computer processor. So locality means that. So this is the large main memory, but the one application or one, sometimes it's called the thread or processor or so program code. So actually, if this one application will not access every location of this large main memory, so I said will not access the every location of this large memory. So what does that mean? So think like this. So if we use some application, so let us assume that we are using the Word application. The Microsoft Word is a word process application, and then actually this Word application can access every file on our storage devices like SSD or HDD. But when you use this Word application, we just focus on the single file because we use the Word for so write something on the file, also edit some file. So with this Word application, so that means even though we can edit many files inside of our storage devices, but for working or for doing homework, so we just focus on the single file. So it's actually the small amount of data. So actually this file is a kind of data, but we just focus on this small amount of data. Then there is also same to the computer application, right? Because the computer application just do what they want, what people want. So do what people want. So the computer application also just access the small amount of data repeatedly instead of access the large amount of data. So the large data equally distributed on this large main memory. Instead of this, the application or program code just access the small amount of data repeatedly. I said repeatedly. This is called the locality. So this is the definition of the locality. The program accesses a small proportion of their address space. So I mentioned that our application just accesses the small amount of data. So then data in the main memory. And then this data is repeated, accessed repeatedly. 반복해서 또 이제 액세스가 된다라는 이거 이해되죠? 우리가 이제 어플리케이션 쓸 때 뭐 숙제 같은 거 할 때 뭐 하나의 파일만 여러 가지 계속 하잖아요. 그거랑 똑같은 거예요. 전체 데이터를 이렇게 하는 거가 아니라. So this is the locality. But we want our memory size is very large, because if the memory size is very large, then we can run our computer system more quickly. But this large data is not accessed frequently. The application just accesses the small amount of data inside of this large main memory. This is the locality. And then I said there are two kinds of locality. It's a temporal locality and spatial locality. Temporal and spatial. So temporal means that if the English word includes the temp or temporal, that means it is related to the time. And then if we use the word spatial, then it is related to the space. So temporal locality means that if the a certain data is accessed by an application, and then the same data can be accessed in the future repeatedly. So that means if this data is used by a certain instruction, then the same data will be if then this same data will be accessed repeatedly. Okay, and then this is called the temporal locality. So let us so a equal 1, then if this variable is declared, then this variable will be repeatedly used in our program. That is the temporal locality. So what is the example of the temporal locality? Instructions in a loop, right? So I said the instruction is also the data, and then inside of the loop, for example, for I, right? And then there are some statements inside of this iteration loop. So these instructions will be repeatedly requested by computer processor. So, and then these instructions locate in the instruction memory, and then that means these instructions are the same instruction that are repeatedly accessed. So this is the kind of temporal locality. And then spatial locality. The spatial locality means that if a certain data is accessed by an instruction, the neighbor data, not the same data, but the neighbor data can be accessed in the near future. That is the spatial locality. It's also obvious. So in our program, we can declare the many variables such as the a equal 1, b equal 2, c equal 3, blah, 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 blah. But these variables will be located actually located in the very close address, because it is used in the same program. So if we use this a variable, then some other statement or some other instruction will use the other variables such as b or c. Also, another example is arrays. Array a like 100. And then if we declare the array, and then if the a0 is used with the high probability, the a1 or a2 will be used in the near future. Okay, so the address is different because it's a different data, but we already learned that when the array is accessed, the array is pointed by offset plus base address. So it's actually the array data it exists in some neighbor location or some close location to the base address of the array data. So if A0 is used, then A1 will be used and A2 will be used. So the neighbor data or neighbor address will be accessed by instruction. This is called the spatial locality. Okay. So items near those accessed recently are likely to be accessed soon in the near future. Okay. The example is the sequential instruction access. So actually, when the instruction is read from the instruction memory, if there is no branch instruction, then the instruction is pointed by P, and then the next instruction is P+4. Then the next is the PC plus A, blah, 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 blah. So neighbor instructions are read from the instruction memory. And then, as I mentioned, the array data is another example of spatial locality. So the data used by a certain application exhibit locality. It's a very important characteristics of our application. Okay, they are actually, this is a very frequently observed what's that, observed phenomenon. Well, we can frequently observe that this similar behavior in our real life. Okay, I will explain when we learn about the cache memory. Okay, but you need to remember that this is very important. So data has the data, actually data shows or data exhibit locality, and then there are two kinds of locality: temporal locality and spatial locality. And then this locality is frequently or widely observed in our normal applications. Okay, it's very, very critical. And then by exploiting this locality, data locality, the memory systems are designed. Actually, the memory hierarchy. So what is a hierarchy? So in Korean, it is called 계층 구조. 좀 어렵긴 하지만 뭐 한국어로는 계층 구조, 뭐 보통 계층이라고 하고, 사실은 우리가 if we say hierarchy, then it's similar to the king, noble people, 귀족이죠, 귀족, and normal people, ordinary people, and servant, slave or slave. So actually, it's the social hierarchy. 약간 부정적으로 들릴 수 있는데, the memory hierarchy is also some different level of memory systems inside of computer systems, right? Inside of a processor. We'll learn about this memory hierarchy, and then actually the memory hierarchy is designed to exploit to make use of data locality. Okay, it's very important. It's very critical. So, so for example, let's think about the main memory. It's a DRAM, and our file. Files exist on our storage. Okay, so then we already know that the size of the file is very large. It's much larger than the size of, actually the size of our storage device is much larger than the size of main memory, right? So usually the size of memory is about 4 GB or 6 GB by 8 GB. But we already know that the storage devices we use about 1 TB or 2 TB or 0.5 TB. So because the SSD is a little bit expensive compared to the hard disk drive. But if we use the hard disk drive, the size of the hard disk drive is normally it's over 1 TB, right? So that means the size of data, actually the every data used by the computer system is stored in the storage device. Okay, and then the size of the storage device is very large. And then when the application is launched, that means we click a certain application, the Windows operating system, or we can also execute a certain application using the command. But if the application is launched, then this application is read from the storage, and then the data is transferred to the main memory. It's also this operation also shows the kind of hierarchy. What do you mean? It's very large. The storage is very large, and then every data exists on the storage. But when a certain data is used, this data is moved to the main memory. But we already know that the size of the main memory is very small. So this is the kind of hierarchy. It's a memory hierarchy. Okay, it's a main memory. So we learn about the cache in this chapter, but also the computer processor includes the very small and fast memory. So for the main memory, we use the DRAM. It's a dynamic random access memory. But inside of the CPU, CPU also includes the internal memory. So DRAM is the external memory. Oops. Because it is located outside of the CPU, but CPU also includes the internal memory, so called the cache. So actually cache. And then for this cache memory, we use the SRAM. SRAM is the static random access memory, and then SRAM is so fast and expensive. Okay. The CPU has also the cache memory. So the cache memory is the small memory, but this cache memory also store the data temporarily. And then we already know that the CPU, the processor also include the register file. So our data is also stored in the register file. So register file is actually the fastest memory in the computer systems. Okay, so actually it's the same memory. So actually data is stored in the memory, but as I explained, these different kinds of memory has different characteristics, and then based on these diverse or different characteristics, we organize some different memory levels, and then these different memory levels are called the memory hierarchy. Okay. So I believe someone already knows about the cache. Okay. The pronunciation of this cache memory is actually the same. It's the same to the cache tone. So I frequently use this symbol to indicate the cache memory, because this means the cache. Then actually the pronunciation is the same. So if instead of the cache, so it's a 5 word, I frequently use this sign. It's a cache. Okay. So I already explained that the computer systems, there are different kinds of memory, and then using these different kinds of memory, we organize the memory hierarchy. Okay. So how can I explain? So let us assume that this is the main memory, and then this is the cache. So this is the small internal memory. Then this is the external memory. So when the processor executes the data transfer instruction, such as the load instruction, then so let us think about what we learned in the chapter 4. Okay, when the load instruction is executed, then which device is accessed? Is the data memory. So then actually this data memory is the cache. Okay. And then as I explained, we already know that the data is the memory. So memory devices has the hierarchy, such as the storage devices and main memory. It's the same to the cache and main memory. So this is the cache memory, but cache is the very small memory. And then the data is temporarily stored in this cache memory. So when the load instruction is executed, then the data is requested from memory, but this load instruction first check the data inside of the cache memory. That is actually the data memory cache. And then I said that this is the small memory. So that means the request data can be found inside of the cache, or the requested data is not found inside of the cache. There are two cases: found or not found, because it's a very small memory. Okay. Actually the every data requested by this load instruction is located in the main memory, but the main memory size is very large, but it's slow. So the computer processor has the very small and fast memory inside of the processor. And then some data is stored in this cache memory temporarily. Okay. So there are two cases: it can be found or it is not found. So if the load instruction accesses cache memory, and then if the data is found, this is called the hit. So hit means that the memory is accessed. So data is requested from the memory, and then if the data is found inside of the memory, accessed memory, then this event is called the hit. So I explain about some terminology of the memory systems. And if the data is not found, that can be also possible, because this is the small memory. It's a small. The request data does not exist. may not exist. The request data may not exist inside of the memory. Then this event is called the miss. Okay, so you need to remember this terminology: hit or miss. Okay, so data is requested by load instruction. So if data is data exists inside of this small memory, cache memory, and then it's found, then data can be provided from this cache memory. Okay, then it's a good case actually. And then if data is not found, then the load instruction check the next level of memory hierarchy, or next level or lower level. And so this is the behavior of the load instruction in the memory hierarchy. So I will explain later about this hit or miss event inside of the cache. Then let's learn about the memory technology and different kinds of the memory devices that are used in computer systems. So 네, 맞습니다. 잘 알고 있네요. 네, 한 학생이 질문했는데, 네, 그 설명이 맞아요. So actually, in our real world, there are different kinds of memory devices. So as I already explained that there is static RAM. So RAM means the random access memory, and then it's called the SRAM. Also, there is a dynamic RAM. It's called the DRAM. It's very famous because the Samsung or Hynix Samsung and Hynix make DRAM, and then the most of the DRAM in the world is made by Samsung and Hynix. Okay, it's a very famous. And then magnetic disk is like hard disk drive. And then sometimes we use the flash memory. So, and then this flash memory is used for SSD. So, and then this slide shows some representative characteristics of these different kinds of memory devices. So this represents the access latency, and it means also the speed or the performance of the memory. And then actually, this is the access latency. So what is the access latency? It's the time required for reading data from the memory. Okay, access latency means that it's the required time for reading data from the memory. So if you see the access times of the different kinds of the memory devices, then you can find that the SRAM is the fastest. So the access latency is about 0.5 nanosecond to 2.5 nanosecond. And then for the dynamic RAM, so DRAM, the access latency is the tens of nanosecond. So magnetic disk, hard disk drive, is about the millisecond. So among these three kinds of the memory devices, the magnetic disk is the slowest, and the SRAM is the fastest. Okay. And then if the memory is fast, that means the characteristics of this memory is very good, because we want the high performance memory. So that means that the access latency is low. So that means the memory is fast. But if the memory is fast, then the price will be, the cost will be high. obvious actually. It's the rule of the real world. If something is good, then that will be expensive. So SRAM is the most expensive. Is the cost for, and then this is the cost of SRAM per gigabyte. It's about $2,000 per gigabyte, and then DRAM is, sorry, and then HDD, the hard disk drive, is the cheapest among these three kinds of memory devices. So it's the performance is high, but the cost is also high. The performance is low, the cost is also low. But what's the ideal memory? So we want performance is good, but performance is high, but we want cheap memory, right? Everyone want cheap product, but everyone wants the high performance product. Okay, right. But this is the ideal case, and then this ideal memory does not exist in real world. That's the problem. So we need to develop some architectural solution for this, the requirement of this memory. Okay. And actually, this slide explain about the DRAM technology, but I believe this is out of the scope of this course. So, actually, the DRAM is the dynamic memory, but in order to explain about the behavior of the DRAM, we need to also understand the internal structure of the DRAM. So it's not simple. So I will skip this part. So, but you can just memorize some different kinds of the clocking method of the DRAM. So usually, so in the processor, I explained that this is the D flip-flop, and then this is the combinational logic. And then I explained that this is the clock signal. So the input of the D flip-flop is sampled at the usually rising edge of the clock. So the input of this D flip-flop is sampled at the rising edge of the clock. But if we see the clock signal, then this is the rising edge, and this is the falling edge. So there are two different kinds of edge, the clock signal edge. So when the DRAM was firstly developed, then DRAM also make use of the single edge of a clock signal, like rising edge. It is called the SDR. Synchronous DRAM was called as SDR. But in order to increase the performance of the DRAM, so recently we used the DDR memory. It's a double data rate DRAM. Okay, so most of the desktop DRAM is the DDR memory, right? So for the DDR memory, this DDR DRAM make use of the both edge of the clock signal, like rising edge or falling edge of clock signal. Okay, and then for the graphics GPU, usually GPU requires the very high bandwidth, so that means the high performance memory systems, because GPUs, the the applications running on the GPU require very large amount of data for parallel processing. So the GPU, the GPU used some special memory such as GDDR. It's the graphics double data memory, but actually the GDDR is the recently the GDDR is the QDR. So it is the quad data rate DRAM. So quad means the 4. So double data DRAM use the rising edge and the falling edge of this clock signal, and then DDR use the 4 pages of the clock signal to read data from the memory. Okay, so now to increase the bandwidth. Okay, so for the QDR, so we can use the clock signal that has the different phase, like this clock 0 and clock 1. So this QDR make use of rising and falling edge of the clock 0, and then also the rising edge and then falling edge of this clock 1 signal. So the clock 1 has the different phase. So why not increase the bandwidth? Bandwidth means the amount of data that can be transferred within unique time. Okay. So there are different kinds of DRAM based on the clock signals. The SDR, so SDR use the single edge, then or sometimes the DRAM, every DRAM that use the clock signal is called the SDR because it means also the synchronous DRAM. Then usually and then currently we use the two kinds of DRAM like DDR and QDR. 이게 좀 헷갈릴 수가 있는데요. 아까 말했듯이 SDR이 이제 synchronous DRAM이라고 또 말을 할 수도 있기 때문에 좀 이게 막 헷갈리게 써가지고 클락을 쓰는 모든 DRAM을 우리가 SDR이라고 또 부르기도 합니다. 그래서 좀 헷갈릴 수가 있는데 어쨌든 지금 현재 우리가 쓰는 DRAM은 DDR 아니면 QDR이에요. 이렇게 이제 생각을 하면 되겠고. So and then this graph shows the cost of the DRAM and then the speed of the DRAM, the performance of the DRAM. So as you can see, the cost of the DRAM has been reduced dramatically because the performance is improved. Okay, that's why we are using very large DRAM. Even the smartphone includes the large DRAM, right? Okay. This time, I will skip here because it's related to the performance of DRAM. But in order to understand the performance of the DRAM, then you need to understand the inside architecture of DRAM. Okay, but it's not simple. But you need to understand the interleaving or memory level parallelism. So it's called the interleaving, or it's called the memory level parallelism, or MLP. Parallelism is the 병렬화 in Korean. So this slide explains the benefit of memory level parallelism or multi-bank system. So multi-banks. So what is the bank in the memory? Bank. It's not the name, or it's not took. So bank is the separated memory block. So you may think like that. This is the separated memory. Okay. So actually the memory is composed of 2D arrays, and then this is the word line, this is the bin line. So actually the data is stored in the cell of memory, and then this cell is located where the word line and bin line cross each other. And then every bit data is stored in this memory cell, a single memory cell. And then in order to read the data from these memory cells, the memory devices has the sense amplifier, or is called the low buffer. The sense amplifier. So this is the structure of a single memory block. And then this single memory block can work separately. Okay. So that means if we give the address is the word address, then the data can be read from the corresponding row of these memory arrays. Okay. This is the structure of the memory. So bank is the actually the separated memory. So some separated memory device. And then, so if you see the DRAM chip, it's a single DRAM chip, but this is the single chip, but the single DRAM chip includes the multiple banks. So that means even though it's a single chip, and then inside of a single chip, we can find many independent memory blocks. So that means, in other words, there are many banks. Okay. And then why does this single DRAM chip include many banks? There are many issues, but the first goal of this memory level parallelism, or the multi-bank system, is to increase the performance while reducing manufacturing cost. Okay. Let's see the three different composition of the memory and processor. So I said that this is the CPU, and then this is the DRAM, and then actually the DRAM and the CPU is connected via external bus. So for this external bus, the DRAM chip needs the pin. It's called the pin of the chip. Also, in order to receive the in order to connect the DRAM with the CPU, the CPU also needs the pin. So pin is the external interface to the external devices, right? And then the cost of the pin is very high. Then so we need, in order to reduce the cost, the manufacturing cost or some the cost of this computer system, entire computer system, we need to reduce the number of pins. Okay. So, but problem is that the memory is the speed of the memory is slower than the CPU. So this is the bus. It's some connection between CPU and the external memory. And then if the bus width is the narrow, then the data transporting data will take long time for this case. Then if the data transfer take very long time, then the performance of the entire computer system will be degraded. So the possible solution is to use the wide bus like this. B. Wide bus. And if we use the wide bus, then we can reduce the data transfer time from the external memory. What was the problem? The cost is high. So the speed of memory is slow, but in order to transfer large amount of data, we need a wide bus. So how can we solve this problem? This is the slow device, but in order to transfer data, this is slow. This is the bus, some connections. Then this is the fast. And then this fast device received some data from the slow device. So how can we improve the performance? If this device is slow, then we can add more slow devices. Right. This is the process. This is the fast. So then this is slow. What is the possible idea? This will take a very long time to read memory from the slow device, but when the data is ready, this data can be quickly transferred to these fast device. Then, what is the possible solution? We split the time. We can split the time, and then for the one time slot, then we just give some command, and then that means the request data from the slow device, and then at in the next time slot, then the request is also given to the another device. And then it will take time. Okay, so clock 1, this request is given to the memory bank 0, and then clock is a CC1. Clock count 2, the command is given to the bank 1. CC3, the command is given to the bank 2. And after a very long time, the data will be ready. Data will be ready by this bank 0. Then this ready data is transferred to the processor. Okay. And then another data from this bank 1 is transferred to the processor very quickly, but it will take a very long time. Understand? So think like this. This is a very slow worker. And we want to get, we want to make use of, we want to increase the performance using the many slow workers. So how? Give request here for the worker 0, and then request at the next clock, the request is given to the worker 1, worker 2, worker 3. So it will take a very long time, but the data is ready after very long time by worker 0. Okay, T. And if the data is ready, then it is given to the processor. And then the request is given after 1 clock. So this worker can work separately, okay, in parallel. So after time T, the data is ready by this worker 1. So this data is transferred to the processor. So same to the worker 2 and worker 3. Okay. This is memory interleaving. So this is called the memory level parallelism. Okay. So if we use the wide memory bus, then the miss penalty. So that means the time for reading data from this main memory is about, in this example, is the 13 cycle. So let us assume that the data, the time for reading data from the slow memory is the 15. But for this interleaved memory, so there are 4 banks, and we can give commands to the memory in the different time slot, like clock. And then after same time, like 15 cycles, the data will be ready. So for this 4-bank interleaved memories architecture, then the required bus cycle is 20. Only this becomes the 4 because the command is given to different 4 banks. Okay. So if we just check the bandwidth, the bandwidth is slightly lower than this expensive system. Okay. And this technique is called the memory interleaving or memory level parallelism. 네, 이거는 지금 굉장히 이제 와이드리 쓰이는 기술이고요. 사실은 뭐 우리의 그 뭐랄까 리얼 월드에 이제 좀 적용을 할 수도 있는 그런 뭐 테크닉이라고도 좀 생각할 수 있을 것 같습니다. How to improve the performance with the many small workers. Okay. Okay. So I think I need to stop here, and then in the next time I will briefly explain about the. I will think about the flash memory. So flash memory is widely used for the storage device because the flash memory is the non-volatile memory. What is the non-volatile memory? The data stored in the memory is not erased even though the power is off for this memory. So this is the non-volatile memory. And then this type of memory is used for storage devices. The flash memory is, recently the flash memory is used for the SSD, and then we already know that SSD is more powerful than the HDD. So usually we learned that the access time, the access latency of the DRAM is about the tens nanosecond. Then the access latency of this flash memory is about the tens microsecond. So about the 1,000 times slower than the DRAM. But it's about, so we already learned that the access latency of the hard disk drive is about the millisecond, tens or hundreds millisecond, but it's 1,000 times faster than the hard disk drive. That's why the flash memory is widely used for the storage devices such as SSD. Then this is the hard disk drive. Then hard disk drive is used some magnetic storage media. And then actually this is the mechanical drive. So that means we need some mechanical component such as the this arm and then some header of the arm. So the cylinder rotate and then the data is read from the surface of cylinder by this header. So this is the mechanical drive, and then because of that, the hard disk drive is very slow, but it's cheap. Okay, so the density of the data is very high. The density is high. Okay. So I think that also we need to skip the hard disk drive because it's the out of scope of this course. Okay. So I briefly explain about the different kinds of memory devices. So I introduced about the memory hierarchy. Also the important things we learned in this today's class is the data locality and memory interleaving, and then some basic concept of memory hierarchy. Okay. Yeah, I stop here. Sorry for late. Do you have any questions? 네, thank you. 수고 많았습니다.